Ok, ¿estamos listos entonces,
Estamos al
Karina?
aire.
Super. Hello, everyone. Thank you so much for joining this last seminar of the fall semester at Universidad de Chile. Today, we have the pleasure to present Edinsson Muñoz. Edison is a civil engineer with a Master of Science at the Universidad de Chile. He is also a Ph.D. candidate in the Hydrogeology group in the Institute of Applied Geosciences at the, I don't know how to pronounce this, the Technische Universität Darmstadt in Germany. So thank you so much, Eddie, for accepting our invitation. It's a pleasure for us to having you here.
Okay, so shall I share my screen?
Yeah, you can share your screen. You can start your presentation.
Yeah, no.
We are watching your the other.
How we did it before?
Yeah.
Yeah, it happens. This one, let's try now.
In the meantime, I want to remind the audience that if you have any questions, you can write those questions in the chat for the YouTube audience, and for the people connecting on the Zoom meeting, you can also write your questions in the chat, please.
Now,
we're watching the secondary screen.
Again, the secondary screen.
Yes. Yeah. Maybe in the okay. Anyway.
There.
Yeah. Yeah.
Now, yes.
Yes. Yeah. So the floor is yours.
Thank you. Thank you for the invitation. Good afternoon in Chile. Good night here in Europe. So today I will talk about some experimental studies that I'm doing in the course of my PhD. And there I related to water quality issues that are present in managed aquifer recharge solutions. So today I will talk about groundwater, and to start, I would like to put a little of context. Groundwater is the most important source of fresh water in the world. When you compare the volume of groundwater to surface water, is much higher. But one important thing about groundwater that I want to mention is not necessarily the volume the important. Another aspect that has been pointed out in literature in the last years is the age of groundwater. The big part of groundwater, more than 98%, is old groundwater determined by isotopic measurements. So when I say old groundwater, I mean groundwater that is older than 100 years. So what does it mean? That is not renewable in the human lifetime scale, let's say. When you take groundwater of that age, you will not see replenish in your life. So that tells about us, about the vulnerability of the groundwater resource, and that's why we have to take care of it. This is even worse when we put groundwater in the context of climate change and also the anthropogenic influence that we are doing in groundwater. The most modern satellite missions that are measuring gravity in the Earth, by means of that, we are able to determine, or scientists have been able to determine that the biggest aquifers of the world are being depleted. So we are losing that volumes of water, and that is even worse when we put in the context of some studies that have mentioned that even low drawdowns, so even low decreases on the level of groundwater in the order of 1 meter can have environmental consequences related, for instance, to flow rates in surface waters, because groundwater and surface water are connected. Another studies have shown that millions of wells in the world have been drying every year. In that context, when we manage aquifer recharge is an important technique. In a very simple definition, managed aquifer recharge refers to several methods that aim to maintain, enhance, and secure groundwater systems that are under stress. Here I took one picture from one paper of Peter Dillon. Peter Dillon works in the CSIRO in Australia, and they have been one of the most important groups in the world dealing with managed aquifer recharge. And in this picture, there are several methods of managed aquifer recharge that I would like to mention. For instance, here we see how you could use small dams in rivers to stop some flow and can generate some infiltration to the groundwater. There are also other techniques that you can take water from river, putting some wells next to the river, extract water from the river passing by the soil as a medium of treatment of water, and then you could store that water for use when you need it. Another technique, for instance, that nowadays are getting more famous is the rainwater collection, for instance, from roof. And then that water you also can use to infiltrate. Actually, my university in one campus, they collect the water from the roof, the rainwater, and they infiltrate next to the campus. But also there are other techniques, and that also depends on the kind of aquifer you have. So for instance, when you have an unconfined aquifer, infiltration ponds are a good technique of infiltration. But in the case of confined aquifers, normally you infiltrate by means of wells. One important technique or one important idea behind managed aquifer recharge is to store the water in the underground, and when you have it, and then use it when you need it. That technique is named aquifer storage and recovery, and also I will talk a little more about that. The paper that I'm citing here is named 60 Years of Global Progress in Managed Aquifer Recharge. I have to say that I disagree a little with the title, because managed aquifer recharge is not something new. It's not something from 60 years ago. Managed aquifer recharge has been always present in the history of humankind. One example for that that I will mention are the pre-Inca cultures in the year 600 after Christ, let's say, in Peru, where they realized that during the dry season they didn't have water. So what they did, they took water from rivers in wet season, they moved by channels, and they infiltrated in other kind of channels and also in hill slopes to delay the flow and then capture in the dry periods downstream. It's very interesting because now Peru, for instance, the city of Lima, a very big city in South America, the capital of Peru, with this study, they try to upscale the technique of the pre-Inca culture, and they determine that if they implement something like this in the water sources of Lima, they could potentially delay almost 100 million of cubic meters per year. Some other more modern examples are, for instance, in the area where I'm living now, is the Hessian Ried in Germany, that is an area close to the city of Frankfurt. Darmstadt, the city where I live here, Frankfurt is there. Frankfurt is one of the biggest cities of Germany. It has a water demand of 60 million of cubic meters per year. But that demand is not obtained from Frankfurt, normally from surrounding areas, and the half of that demand is obtained from the Hessian Ried. The Hessian Ried is an alluvial plain where the boundaries are the Neckar River, the Rhine River, and the Main River. And it's an agricultural area of very intensive agriculture, but from here, from Bibelsheim, the water is taken and moved to Frankfurt. How they do that? Well, here I show a scheme. They make riverbank filtration. They take water from the Rhine River. They make water treatment to drinkable water standards. And after they collect this water, they infiltrate in the aquifer. For instance, here as an example, I show a scheme of an infiltration trench. They put this water in the aquifer, and when they need it, or when they require, they take it out by wells. Those wells are connected to pipes, and those pipes provide water to Darmstadt, 50 kilometers away to Frankfurt, and also to the agricultural land close to this zone. How much water they took? They took around 50 million of cubic meters per year. That represents a very low amount of the average Rhine discharge. And they started to do this in 1989. Here I show some pictures of the infiltration trench that they have in this area. They also infiltrate by large diameter wells, and also former drainage trench in the past. Now they use also for infiltration. What they achieve in this region doing this, that they are able to control the water levels of the aquifer. They have an extensive monitoring network, and in every well, thresholds are defined. So they only pump when they are above the lower limit. And by means of this, they have been able to control the aquifer. And in the last 20, 30 years, they have almost a constant level or with low variation controlling with this monitoring network. So with this, I try to say that also managed aquifer recharge is a tool that allows us to control the volumes of water and the levels of aquifers. Another example that I would like to mention that also was part of the project where I was working is Israel. Israel is a country located in a difficult area in the Mediterranean Sea in the sense that they don't have too much rain. They have the half of the country is actually almost a desert. And because of this, Israel has had to develop many facilities. In the 60s, they developed, for instance, the National Water Carrier to take water from the Sea of Galilee and to move to the south. But also they were relying a lot in two principal aquifers, one coastal aquifer and the Western Mountain Aquifer, but principally was in the coastal aquifer. And in the 60s, they realized that the water levels were very, very low, and they had to do something, and they started to make managed aquifer recharge. So in a not that big area, they have 3 facilities for managed aquifer recharge. One is Menashe, the other one is Chavdan, close to the city of Tel Aviv, the most populated area of Israel, and another is Chigma. Depending on the site, they use different water sources to infiltrate. In some of them, they have winter floods, the water that they have in winter in the hills, they collect and they infiltrate, for instance, Menashe. But since now Israel uses a lot of desalinated seawater excess, actually it was supplied the most of the demand. They also infiltrate when they have some surplus. And in the case of Chavdan, they infiltrate secondary treated wastewater. So now I will show a little more of this facility. The first I want to show is Menashe. Menashe is to the north of Israel. They collect the water from in rainy season from the hills, and they move to some infiltration ponds in the coastal aquifer. And since 2015, they started to also infiltrate the surplus of the desalinated seawater. In average, they are able to infiltrate 10 million of cubic meters per year. And something very interesting about this field is because they infiltrate now desalinated seawater that has a different isotopic signature to the one of the rain and the aquifer. So they are able to model the infiltration of water because also they have a very extensive monitoring network there. And that is something that I want to say. It's not just put water on the ground. And also, as I shown in the case of Germany, you need to have monitoring. You need to be aware that in any moment you can face problems in managed aquifer recharge. So it's very important to have some tracer. And in this case, Menashe use the deuterium of both waters. The biggest facility they have in Israel is Chavdan. This is another one. And this is much more interesting because they is connected to a wastewater treatment plant. They collect the sewage of 2.5 million of inhabitants in the metropolitan area of Israel, close to Tel Aviv. That sewage goes to the wastewater treatment plant. Here you have like the biological reactors. After that, the water goes for some clarification and then goes to infiltration basins. In that field, they have around 50 infiltration basins where they infiltrate the water. In this sense, the soil becomes a tertiary treatment because the soil has property to even increase the quality of the treated wastewater. After the infiltration, when they need it, they have around 150 recovery wells where they can take water with better quality than the one they infiltrated. What they do with that water, they recover, then they move that water to the south of the country for agriculture. So Israel, doing this, is able to make agriculture in the desert. They infiltrate around 130 million of cubic meters per year. To put this number in a context, this is more than the half of the reservoir Puclaro in Chile, more than the half of the reservoir El Yeso. And they infiltrate 130, but also when they recover, they are able to recover a little more because also they get some natural recharge happening in the basins. This is the bright side of managed aquifer recharge, but also there are some problems, and actually that is what I want to talk about the rest of the presentation. Something that they have done is that they have present in the water after the secondary wastewater treatment plant, they have presence of pharmaceutical in the water. One example that was more in deep study was one anticonvulsant drug that is named carbamazepine, that is used as an antidepressive, as an anti-epileptic, and they realized they have that compound in the recharge treated wastewater, and even after the tertiary treatment, that is the soil aquifer treatment, they also still have it. Then they went to study the soil, and in the soil they realized they also have that compound in the soil, and they had more of this compound where they had more organic matter. Now the question is this problem of carbamazepine or any pharmaceutical only in treated wastewater? The answer is a clear no, because nowadays, and also this was published last year, we have presence of pharmaceutical compounds in almost all the rivers of the world. This study was a worldwide effort where they took samples of in rivers of 104 countries, and they detected pharmaceutical almost in every country they studied. As you can see here, the compound most found was the compound carbamazepine that I mentioned before. Here they studied a suite of 30 compounds. That doesn't mean that the others were not there. That is just they didn't look for those. And interestingly, another thing is this is the first study that shows pharmaceutical pollution also in Chile. They took samples from the Mapocho River, from the Maipo River, and they also found presence of pharmaceutical active compounds. How the pharmaceutical reach the environment? Well, we have to be aware that nowadays we have more than 4,000 pharmaceuticals used by people. Every year we are creating more. There are multiple pathways, but mostly or the most important is the excretion by users, and with users are not only humans, also animals. And also this is related to wastewater treatment. For instance, in poor countries where you don't have wastewater treatment facility, the sewage goes directly to water bodies, groundwater or surface waters. But also in developed countries, when you have wastewater treatment plants, normally wastewater treatment plants, they discharge in rivers. So that's why you have presence of these compounds in surface waters. The important thing here is even at low concentration, because we talk about nanograms per liter or micrograms per liter, this can affect organisms in the environment. And for this, I show the first study that pointed out the danger of pharmaceuticals. In Pakistan, in the 90s, at the end of the 90s, they realized that vultures were dying, and there was a population decline of these birds greater than 95%. They didn't understand why. They started to take samples of the inner organs of these animals, and they detected diclofenac in the kidneys of these animals. After the research, they realized that this was because the animals that vultures eat they were fed or they were taking diclofenac as an anti-inflammatory. So even in low concentration, these compounds can be dangerous. What is the problem we are facing with this? Some of the compounds are easily degradable. That depends on the structure of molecules. For instance, paracetamol is a compound that is easily degradable in the environment by bacteria, but other compounds, as I showed, carbamazepine, for instance, are not possible to degrade. Do we have a solution for this? Well, we are studying that. Some advanced water treatment techniques, such as membrane filtration or advanced oxidation processes and reverse osmosis, they have shown that they are able to take out pharmaceuticals from water, but the problem that is are very expensive techniques, and not so many countries can allow to use these processes. So now the attention is in other cheaper treatment techniques that, for instance, activated carbon, that is used normally in water treatment plants for absorption of compounds and contaminants, and also biochars that are more friendly produce activated carbon. Also, some attention now is in nature-based solutions that, in very simple words, means soil plus biology trying to degrade compounds. In that sense, for instance, USA have tried since many decades ago to treat wastewater with contracted wetlands, and also, as I showed just recently, the soil aquifer treatment of Chavdan. But as I said, there are compounds that are not degradable, so not necessarily this is a solution, and that's why the scientific community is studying this. So this is the reason, or this gives context to my PhD and to the experiment that I'm going to show, because we need to study how pharmaceuticals transport in soils, and also we need to study how they can be remediated. So the first experiment I would like to show, this is a collaboration that we did with the Polytechnic of Catalonia and also with the University of Frankfurt, is what is the role of soil biofilms in the fate of pharmaceuticals. And for this, we did some column experiment, but maybe first I should mention what are biofilms. Biofilms are the structure where bacteria live. When bacteria make metabolism, they start to organize, and they embed in a self-produced matrix of insoluble extracellular polymeric substances. I will mention this as EPS. So the EPS grows in the soil and can cover the surface of the grains of soil, as I show here in this picture. Since they cover the underlying material, they can reduce the hydraulic conductivity. That is a phenomenon known as clogging. And also, they could influence the sorption behavior of soil, because since they cover the surface of the soil, they change the physico-chemical properties of the grains of soil. And this was the idea that was raised to this study, because our hypothesis is this biofilm could change the behavior of sorption of soils. So for that, how you deal with biofilm in soils, or how you can model that, or how you can conceptualize that. Biofilms, even they are a gel type substance, and I say that they have polymeric substances, they are more than 90% water. So when the biofilm grows and covers the soil, here you have one portion that is more than 90% water. So in a way, it's a porous space also, but it's not moving because it's attached to the soil. So this is conceptualized, and Van Genuchten proposed this some decades ago as an immobile porosity. What does this immobile porosity? It changed the typical advection dispersion equation, because now you have a mobile phase where water is flowing that move but advection dispersion, but also is exchanging mass with this immobile region that could be, for instance, biofilm. That phenomena is a diffusive phenomena and is controlled by the omega, by this rate that is named omega, and that is the term that you see in this equation. So you have one transport equation for the mobile phase, and you have one equation for the immobile phase. When you don't have advection, you only have this diffusion. This is in terms of conservative processes, but also could happen sorption or degradation of solutes. So to deal with that, normally what you do, you make conservative tracer experiments to determine the conservative transport parameters, and then you put your non-conservative solute, and then you try to determine retardation factors that are related to sorption or degradation rates. So with this idea in mind, we built columns, we did saturated columns, thinking in groundwater, but with the idea to develop different conditions of biofilm and of biological activity. For that, we collected the soil from the Hessen-Ried, the area that I already talked, that I showed has some facilities of managed aquifer recharge, and also it has a good percentage of organic matter, and also showed in Chavdan, for instance, carbamazepine sorb in organic matter. So we also wanted to have that. As influent water, we use synthetic wastewater diluted. We didn't use real treated wastewater because you have so big variations of concentration of pharmaceutical that we prefer to have everything more under control. So we prepared this synthetic wastewater with tap water and some nutrients, and we didn't contain pharmaceuticals. We ran 200 per volumes. The columns were running more than 1 year to condition all the biomass inside of the columns. We were monitoring continuously the whole period of the experiment, pH, redox potential, and pressure, also to have an idea of clogging. And we made some tracer experiment to determine the conservative parameter. For that, we inject sodium bromide as a conservative tracer. And in some moment after this 200 per volume, we injected pharmaceutical. What had every column? So one column had the soil natural, as we took from the field. We feed it with this synthetic wastewater, but also then we replicate that column, and to the water we added some bactericide, sodium azide, that is commonly used in this kind of experiment, to decrease the level of biological activity. And to analyze also a little better the role of organic matter, we remove the organic matter for one column, and you do that burning your soil at 550 degrees. With that, you burn all the organic matter. That's how it looks in a scheme, but that's how it looks in reality. You can see all the mess with the cables that to be monitoring the continuous variables. Which compound we use? We use carbamazepine because, as I said, it's not degradable and it's a compound you find everywhere. We also use diclofenac, and also we use metoprolol. Metoprolol is an antihypertensive agent that people take to control blood pressure. But the reason behind this was not only the use of the compounds, is that pharmaceutical, depending of pH, will change the speciation. Pharmaceuticals are able to, the pharmaceutical compounds are able to release protons or capture protons according to pH, and that is related to the acid-base dissociation constant. And we wanted to have compounds of different speciation. Analyze pharmaceutical is not that easy, because since you work in low range of concentration, normally you need to hyper-concentrate your compound, making solid phase extraction. And then when your sample is hyper-concentrated, then you can inject in a liquid chromatograph coupled to a mass spectrometer. So a very complicated analytical method to measure pharmaceuticals. What we saw with the redox potential, and first here I will jump one slide and then I will come back. Why redox potential is important? Because when you are talking about organic chemistry, most of the redox reactions are mediated by microorganisms. They are a redox phenomena, so where transfer of electrons are involved. So for instance, when this is the formula of the dissolved organic carbon. So here, for instance, you have the oxidation of organic carbon, you have the nitrification, manganese release, iron mobilization, or sulfate reduction. All of them are associated to some energy, some give energy of the reaction that those can be expressed in terms of some voltage. So according to the voltage you measure with redox potential, you can have an idea what kind of reactions are happening in your system. What is important about redox potential? Redox potential has to be measured in situ. It's not the same when you take the sample from the groundwater and you expose to the atmosphere, because you will have oxygen diffusion, and that will change your measurement. So it's very important you measure in situ as we did. In that way, redox potential is also a measurement of the biological activity. And we saw in our first column that had the organic soil with the diluted synthetic wastewater, we saw more reducing conditions after an oxic zone. That means that we have several electron acceptors working in the column. The column with the bactericide showed higher redox potential. That means you have less biological activity, and the column without organic matter was almost oxic before the injection of pharmaceutical. The injection of pharmaceutical is the period between black lines in every column. And then we saw some change to reducing conditions, and that was due to the use of some methanol to dissolve the compounds. And even the increase of concentration of dissolved organic carbon was very, very low, less than 10%. We still saw that change in redox condition. That means that even we didn't think we had some biology here, already we had it. To complement this, at the end of the experiment, we analyzed the EPS content of the biofilm, so this substance where bacteria are embedded, and we saw that for this column, we had a little increase, so little production of biofilm, and in the context of the column with organic soil, we had some initial content of biofilm that it didn't change too much in the column with the bactericide, but we had a statistically significant increase in the column with more biological activity. So with this, we were able to achieve what we wanted, to have different biological conditions in every system. What happened related to the fate of pharmaceutical, where we injected 44 volumes of this, and then we modeled the breakthrough curve, so the elution of the compounds in the outflow. Here, the dotted line shows the conservative transport model, so without considering sorption and without considering degradation. So you see, it's not a good fit, but when we activate retardation and degradation, we fit okay all the compounds. So for some of the, we didn't see degradation for carbamazepine, was expected because of literature, but we saw some degradation for metoprolol and diclofenac. But now the question is, where, in which compartment? Was in the mobile porosity or in the immobile porosity? So then we integrated the equation that I showed at the beginning of this section. And in the case of the soil with more biological activity and with more biofilm content, we were able to see that the immobile porosity, what we link to the biofilm content, was able to sorb carbamazepine, diclofenac, and also metoprolol. We saw, because of this, with the importance of the immobile porosity for column 1 and column 3, we are able to propose and suggest that biofilm could act as a sorbent that we see here in the immobile porosity. Second study that I would like to show, since I mentioned that pH is an important parameter when you study pharmaceuticals, we wanted to study the effect of pH in sorption of some pharmaceutical in different organic sorbents, because as I mentioned before, it's a cheaper technique to try to deal with these compounds. This time, this was a collaboration with the National Laboratory of Civil Engineering in Portugal. So we use sorbents to make batch experiment with them. One sorbent we used was biochar, that is produced by wood, but then you make pyrolysis at high temperatures, but in an inner atmosphere, so without oxygen to avoid combustion. And with that, what you do, you change the structure of carbon and you start to create a porous space inside that gives you big surface area that is a relevant variable for sorption. The difference of activated carbon is normally you have a physical or a chemical process of activation after this pyrolysis that increase your surface area. And we also wanted to use something better than activated carbon, and for that we use colloidal activated carbon, that the diff is a powder activated carbon, but wet grinding. With that you achieve a smaller particle size, so higher surface area. And this is an innovative remediation technique. Actually, we wanted to buy for some company that was selling it. They didn't want to sell because they don't sell for research, because they make money with it. But luckily, we got something similar from the Health Home Center in Leipzig. Why is so innovative? Because of this very small particle size, you can create suspension that you can inject in soils. So the idea of how people are using this, or how companies are using this, they create suspension, they inject in soil. With that, they cover the grain of the soil with carbon, and they use that for remediation of compounds. We characterize the chemical properties of this sorbent. The higher element composition is carbon, and the specific surface area where, as we expected, so biochar has a low specific surface area that increases with powder activated carbon, and is even higher for colloidal. And that is related to the pore volume that has your sorbent. The pore volume is the space that you have for sorption. Another important property when you study sorption is the isoelectric point, the number that I have here and determined by this. The isoelectric point is the pH when the surface of your sorbent, or the particle of your sorbent, doesn't have a charge. And below that pH, your sorbent will be charged positive, and above that pH, the sorbent will be charged negative. Since the pharmaceutical, they also have charge, is a very important parameter to understand, for instance, electrostatic interaction between molecules of pharmaceuticals and solvents. In this case, we use different pharmaceuticals, because also since we did batch experiment, we could work in a higher concentration range. And this time we use ibuprofen. Why we choose ibuprofen? Because it's one of the pharmaceuticals that people take more. I think everyone has taken once in life. And we also choose sulfamethoxazole. Sulfamethoxazole is an antibiotic. And antibiotics are a big problem because the biggest population on Earth are bacteria. So when you have antibiotics in the environment, you are creating resistant bacteria to antibiotics. So that is a problem that the scientific community is quite aware and quite worried. In this case, because also in the columns experiment, we saw that anions compounds are more difficult to remediate. We choose these two compounds because also they have neutral anion speciation. To explain a little better this, I will show this scheme that, for instance, show the structure of sulfamethoxazole, the three compounds, how they behave in pH. Carbamazepine is always neutral, and sulfamethoxazole, if you are pH lower than 1.6, you will have this group charge positive, so your molecule will be charged positive. After that pH, that proton will be released, you will have a neutral molecule, and in a pH after 5.8, you will have that proton released, and you will have a negative molecule. The same happened to ibuprofen. After pH 4.9, that proton is released, and your molecule is negative. This acid-base behavior of the pharmaceutical change also another chemical properties, for instance, the solubility of compounds and the log-D. Log-D is an important parameter because it's a chemical measurement of the hydrophobicity or how hydrophobic is a compound. When you have a high log-D, that means that you have your compound has a big affinity to organic surface, but when it's low, you prefer to stay in water than go to a solvent. So because of this, we were expecting that at pH 8, for instance, the absorption of sulfamethoxazole and ibuprofen should be lower. As I said, we study this phenomena with batch experiments. The size of the batch experiment depends on the solvent. Since biochar has lower surface area and lower pore volume, you need a higher concentration to achieve sorption. In the case of powder activated carbon and colloidal carbon, we had to use bigger batch and lower masses. And how we did it, we tried to fix the pH first, fixing the pH, then we spiked it with pharmaceutical, and after 7 days of equilibration, we took samples, we filtered, and we injected directly in another kind of machine that was able to detect higher concentration. We had a target pH level, pH of 4, 6, and 8, tried to cover environmental ranges and also the pH where the charges of the compounds change. What we have seen, and I'm working on this, well, normally you study sorption by means of the sorb concentration that I'm defining here. The data with lower sorption is the data of biochar. And here you can see a very wide variation depending on pH and substance in sorption. This is how normally literature people study sorption, relating the concentration sorb with the concentration in equilibrium in water. But the problem of this is that you are comparing not normalized variables. So some studies have used also the solubility of the compounds to normalize the sorption. And when you do that, you can see clearer how, for instance, at pH 8, the compounds in the biochar and also in the activated carbon is lower. Interestingly, carbamazepine, that is a compound that doesn't have charge or doesn't have a change in charge. Also, you have some difference in sorption, even that has not a change in charge. And we are attributing this to some competition. When you are at pH 4, ibuprofen, sulfamethoxazole, go to your sorbent, leave less space for sorption of carbamazepine, and that change at pH 8. That is an evidence of competition. We fitted isotopes of this data. In the normalized version, we were able to fit 27 isotopes, where we see a strong nonlinearity that in simple word means that you have a pore filling process, so the compound go to the pore space of the solvents and they get stuck there. Another thing that has been done in literature is try to relate another variable that relates the source concentration with the concentration in water that is named the partition coefficient, or KD. The KD in some studies has been linked for other organic acids as ibuprofen and sulfamethoxazole R, has been related to the log D. And in our case, when we don't see that effect, and the difference is that this kind of relationship were made in studies only using one compound and not using more than one compound or under competition, because as we did, because we use the 3 compounds together. And actually, if you think in real condition or something closer to reality, you don't have 3 or 4 compounds, you have most likely 1,000. So here we are planning to say that this kind of relationship are not useful, as the problem is much more complex than we thought. The last experiment I would like to share with you is another collaboration that is in the context of the PhD of one colleague of mine, that we built some big tank experiments in the National Laboratory of Civil Engineering in Portugal, in El NEC. And here we use real treated wastewater and also real groundwater to try to study the interaction and the mixing processes between these 2 waters. We built 3 large tanks. Here you can see the dimensions, almost 3 meter length and 2.5 meter of height. So here we injected real groundwater. We were able to collect groundwater from the campus of El NEC, the groundwater they used to irrigate the garden there. And also my colleague went to collect every week real treated wastewater from one Lisbon wastewater treatment plant. So we had a continuous flow of groundwater here, and some 1, 2 or 3 times per week, we were infiltrating some treated wastewater here and allowing this to flow in an outflow that we have controlled here. This experiment was unsaturated. We tried to emulate real managed aquifer recharge sites. And first, we didn't use the 3 tanks first to learn on how it's not easy to deal with so huge experiment. We only used 1 tank, and we put all the sensors we had there. We put 5 redox probes that in total make 90 redox sensors inside of these tanks. We put, as I said, was unsaturated. We measured soil moisture in 5 points. We took measurements of electrical conductivity in inflows and outflows. We built 3 wells. And in these 3 wells, we took samples in 3 points per each well to analyze what was happening between the water entering here and the water flowing with the groundwater. We also took samples of the unsaturated zone. We used tipping buckets as flow meters. Normally, tipping buckets are used to measure or to account for rain, but since groundwater are low flow, also were useful for us as flow meters. We took samples to analyze dissolved organic carbon, major ion, trace elements. In this case, we didn't work with pharmaceutical in this tank. We studied just nutrients. We were running this experiment continually for 6 months, and we used quartz sand. So here you can see we were playing with this experiment a little. At the beginning, we infiltrated quite continuously wastewater and flattening with a high flow rate of groundwater. Then we realized that to see more things was important to give more residence time to the water. So we decreased the amount of groundwater to don't flash so quickly the treated wastewater. That's how it looked, that tank in reality. Here you can see the multi-wells. This is a redox probe with sensors inside. And well, there were also here there are some pressure transducers also. And here the suction cap takes water from the unsaturated zone. We were able to interpol because we had a lot of redox sensors, and as I said before, they are important to give an idea what kind of biology is happening there. We were able to interpolate that. We did some kriging with that data. And just to show some example, at the beginning of the experiment, in the first 15 days, we had more or less oxic conditions inside of the tank. And during that condition was in the same time, we had some ammonia in the treated wastewater, and that ammonia under oxic conditions is transformed in nitrate. So we had nitrification, but then we gave longer residence time to the water, to the treated wastewater. We achieved more reducing conditions, and in that time we were able to see some the nitrification. We did some mass balance, and in those mass balance, you take your inflows, your outflows, and then the rest is stored or transformed or degraded. We prefer to use the word transformation because not necessarily you degrade something, you transform in something else. So this redox potential with this can give us an idea, but we are not able to distinguish precisely between storage and transformation. So for that, we also did some numerical modeling of the experiment. We did some unsaturated flow and transport modeling in FIFLOW. And here, for instance, we show this is a plume of the one injection of treated wastewater. This is how it looks after 1 day, after 4 days. And then when you start to flush with groundwater, after 7 days, you have a plume like that. It was very important for us to understand what will happen in the experiment. And we will use this conservative transport model, or we are using this conservative transport model, trying to describe better what happened inside of the tank. So we applied that chloride. Chloride normally in groundwater is used as a conservative tracer because it's not a reactive compound or doesn't react so easy. So we achieve a good fitting of the model for chloride. And then we apply the same strategy, for instance, to nitrate. And in nitrate, you can see when we model a conservative nitrate, there are points, for instance, here and here, that where we are not able to fit what we saw. So this is the evidence where the nitrification happened. And we had some nitrification at the beginning, also at the last period of the experiment. But also we had, for instance, with this, we are able to say, okay, we had some denitrification in some parts of the experiment happening. Finish the last experiment that we will run, build it, but still is not running. We hope in the next month start to run. Now we will use the 3 tanks. In 2 of them we put reactive barriers. One barrier that we put is biochar, the same biochar that we use in the batch experiments. So we mix 50% volume, the quartz sand with biochar, and we implemented one reactive barrier in the infiltration zone. And as I showed before, organic matter is an important solvent. So we wanted to use an organic barrier. And for that, we use compost that we also mix 50 and 50%. Since the lesson that we learned with the first tank, we will use low flows of groundwater, and we will try to give more recent time to the treated wastewater inside. And we took our sensors, we distribute in the chambers. And now for this experiment, we will analyze pharmaceutical, and we will try to see how good are they to sorb or to degrade pharmaceuticals. With this, I'm almost finishing. I want to acknowledge my university, the institute where I am in the Applied Geoscience group, of the Hydrogeology group, and also to the Civil and Environmental Engineering department of the university. I want to acknowledge my supervisor, the 2 institutions where I stayed for second-man internship during my PhD, to the entire project, and also to the European Union to give the funding for this project. Here is the website of the project. Here is my email if somebody wants to ask or discuss something further. And to finish, I would like to give just some comment. Normally when people talk about managed aquifer recharge, people talk about volumes, about water quantity. Here in this presentation, I show some problems of water quality. As I said at the beginning of the presentation, groundwater is salt, it's not a sustainable resource. So whatever we put in the ground goes to the groundwater and most likely will stay there. And here I want to use the term that one famous hydrogeologist, John Cherry, used in one presentation that I watched once, that we have to be careful with groundwater because we are converting groundwater in a chemical soup. That is my last words. Thank you for your attention.
Thank you so much, Eddie, for your presentation. It's quite interesting, actually, the chemical soup, how we are, I don't know, modifying all the environment and how that is affecting us is, well, who knows, right? I would like to remind the audience that you can write down your questions in the chat. people in the Zoom meeting, but also on YouTube. There is a little delay with the YouTube broadcast. So I don't know if Professor Mendoza, do you have any questions? Because I have some, so.
Yes, I actually have a couple of questions. So thank you, Eddie. Very interesting talk. So the first question is related to one of the, at the very beginning of your presentation, you talk about the deuterium, that it was used as a tracer. So my question is, like, how do you choose the tracer, and what other options do you have depending on the problem that you're addressing?
Yeah, well, normally to choose a tracer, first of all, it has to be something non-reactive. So as I told, for instance, in the tanks in Portugal, we use chloride, but you need to have normally some contrast between your two waters. So you name that end members. So for instance, in this case, they had a very different signature between the desalinated seawater and the aquifer. So because of that contrast, you are able to model and see some changes. When you have, for instance, if the water would have the same signature, then deuterium is not a tracer because you will not see changes. So it will depend in the contrast of thing you have, and it has to be conservative. Normally people use chloride, and we use, for instance, in the tank in Portugal, because the chloride of groundwater and treated wastewater was different. In the case of Israel, they use deuterium, but for instance, you cannot use tracer chloride as a tracer in the salt pans of Chile in the north, because the concentration of salt is huge unless you are infiltrating something without chloride. So normally you look something with contrast.
Okay, so I presume that you would choose different tracers depending on where you are in Chile, for instance.
Yeah, most likely, yes. It will depend what kind of water you're mixing, but you need to have a contrast to determine that.
All right, thank you for the answer. So related to that, like, how do you envision possible applications of all your work, your experimental modeling work, to problems of groundwater quality here in Chile?
Well, first of all, we should define the problem in Chile. As I said, there are not so many studies dealing with this. I mean, first of all, I would like to see how big is the problem. For instance, I can imagine a wastewater treatment plant as La Farfana, for instance, would be very interesting to know how much pharmaceutical you are discharging. And then you need to implement some treatment. So for instance, we are doing in Portugal, implement some layer before you put the water in the environment, the treated wastewater in the environment. Also, you can, for instance, as I told, pH is very important. You could play with pH. I mean, also you could, when you make, there are some infiltration ponds in Chile. You should choose, for instance, reactive barrier. Spain has done that. One of the studies that I showed, where they used redox potential probe and they modeled redox potential, and when I showed the reactions, they have implemented there, for instance, reactive barrier. They put compost in the ground before the infiltration, and they started to understand how improve the denitrification, how improve the absorption of emerging organic contaminants. So at the end, the idea would be implement reactive barrier when you are infiltrating water. But that will depend on the source you use, and in that sense, I think Chile still don't know too much how big is the problem or not.
Okay, I understand.
Very concerning, by the way. I mean,
yes.
We don't know what the problems are. It's, yeah.
Yeah, it's kind of disturbing. Okay, so my next question is related to synthetic wastewater. How do you actually produce it? Like, how difficult is to create it, and how long does it take?
It's not that difficult. Well, there is a recipe, not like I invented the recipe. There is a OECD guideline to work with wastewater. So you can create synthetic wastewater. You use some nutrients. You use amino acids. You use urea. You use proteins. So it's just chemical that you buy. You mix it. But the problem is, normally when you put several nutrients in water, because tap water, even if a clean resource, you also have bacteria there. Normally you will not have oxygen in your water. Actually, something that I didn't mention, we create the water and then we had to put air to equilibrate the water to reach oxy condition before we inject it to have some constant level of oxygen and nutrients in our water. So it's not that difficult. It's defined by some recipe, quite used in literature. You just need to buy the nutrients, mixing, and then equilibrate it, as I did with some air for some time. The problem is when you have a long-term experiment running, the water is stable just for a couple of days, so you have to create every week. I was 1 year every week creating this synthetic wastewater, 20 or 40 liters to inject in the columns, and not more than that didn't last more than 1 week. Other studies, they create this water and they put inside of a fridge to keep more or less the biology quiet, let's say. So it depends on your case or your resources is what you can do, but it's not that difficult to create.
Okay, thank you for your replies. I have no further questions.
There are some questions on the chat in YouTube. So this is a question by Eduardo Rubio. He says, "Hi Edison, thank you for your presentation, very interesting. And thinking on a public policy for Chile, and especially regarding the groundwater contaminants, what do you recommend for obligatory or mandatory monitoring?"
Oh, well, good question. The last time I saw the regulations of groundwater, there is a very little list of pollutants. Yeah, and normally when you see guidelines of Chile, you're like, okay, if it's not referring the Chilean guideline, go to the Australian one or go to the Swiss one. When you see the list, normally I would go for the easy to the difficult things. One thing that you should take care first is about trace elements, like trace metals. For instance, to be honest, I don't know what are the regulations of arsenic in Chilean groundwater or uranium in groundwater. First, I would go for those kind of regulation. Related to the topic I was talking about, organic pollutants, there is no regulation in the world. Just last week, I read a news that the European Parliament, they were trying to create a watch list of pharmaceuticals in the environment, for instance, but the list is 20. I just said that there are more than 4,000. So in a country like Chile, as water quality, I would take care first of trace elements. About nutrients, it's not good to have huge amounts of nutrients, for instance, nitrate. For instance, here in Germany, nitrate is regulated. You can't have more than 50 milligrams per liter in groundwater. Germany received a fine from the European Union because of higher levels of that. So something that they would regulate, I think in the south of Chile, when you go to agricultural lands, I don't have any idea. There are not so much monitoring how much nitrate there. Most likely when you use fertilizers, you will have much more than 50 milligrams per liter. So I will go for nutrients. I will go for trace elements. I would start to study these kind of compounds. I talk just about pharmaceutical, but there are other compounds, organic emerging compounds that are even more dangerous. There are compounds that are named PFAS. They are used in military bases, in industries. I can guess that the mining industry in Chile also have many of them because they use that for polymers to create polymers. And those polymers are very cancerogenious. That is very, very proof in literature. So I would start easy. I would try to see nutrients, trace elements, some biological parameters maybe, and try to study which kind of pollutants we have in our waters, because nowadays in Chile, we are almost blind in terms of these emerging organic pollutants.
Thank you. And Eduardo also has another question. The question is, if we don't adopt a good measurement of these parameters, what can you predict or expect if we take into account the climate change?
What we expect in terms of groundwater with climate change, you mean in Chile, we don't implement guidelines?
Yeah, and we don't monitor groundwater and, well,
no,
like,
well,
yeah.
climate change is affecting us in terms of volume more than anything else, I would say. I mean, when you have less groundwater or you have some evaporation, for instance, of groundwater, you have an increase of concentration because of that. I would be more careful with to be honest, with the anthropogenic effects or in groundwater more than climate change, because for instance, I would be more concerned about discharge of mining sites in groundwater, about landfills, about agricultural sites. But well, now also climate change are affecting soils, not only groundwater. So in that sense, now our soil, they retain less water, they are getting drier, and that also avoid recharge. I mean, that you saw in the last flooding event that Chile had in the last 2 weeks ago, when your soils are dry, the water don't infiltrate, remove sediment from the riverbed, and there you have big problems.
Yeah, and I have a question just regarding that, because you mentioned that climate change will affect the volume of the groundwaters, right? But you were talking about solutions that increase the recharge in aquifers. So do you have any idea what is the ratio of the natural recharge, which is going down in the case of Chile because of climate change, and how these alternatives can contribute to increase the recharge in aquifers?
I mean, when you try to increase the recharge, again, your volume of water is similar. What you are doing is like something like I showed with the case of Peru. You delay your water. I mean, when you increase infiltration, it's like you are creating reservoirs underground. Yeah, of course, with climate change, we have, and that is something that I've seen here in Europe. For instance, you go to some facilities of managed aquifer recharge. I've been in Barcelona, and you go to the river where theoretically they take water to infiltrate, and they don't have water to infiltrate because the flow rate is too low. So you don't have the ecological flow rate. So in that sense, you will have less volume of water to infiltrate. That is something that even you make. So the idea would be like the same that happened in Chile like two weeks ago. You should be prepared when the water comes. Now with climate change, the water will come less, but when it comes, will come a lot and will come very, very hard. And now you have the isotherm zero moving up, so you have more rain, less snow. So you have to be prepared for those cases. I mean, try to be prepared when you will have water, and in that moment, try to infiltrate. And that is something that also you should include in cities in Chile. For instance, when you see something that happened in Licanten, I also live in Chile in a small town. They are almost only concrete. You don't have green areas. You don't have any part of the city to infiltrate. So things like that, we should be more aware with climate change, I would say. Be prepared because we will not have water, but when we have, being able to store and hopefully also a part of that in the ground.
I think we are on time. I don't know if Pablo has more other comments. No? So there are no more questions in the chat. So thank you so much, Eddie, for your talk, for your presentation. That is very interesting. I didn't know about the pharmaceutical problem in groundwater, so it was very illustrating.
Not only groundwater, not only in groundwater.
Yeah, not only groundwater. Yeah. So thank you so much and for accepting our invitation.
Okay, no, you're welcome. Was a pleasure. Nice to see you also.
Bye-bye.